See, in this molecular orbital theory of simple diatomic molecules, these are the questions that how to distribute the electrons, how to make the energy level diagram. So I think I have showed you some energy level diagrams. Also, how to make, depending on the structure, you can number of electrons you can make. If less than 14, then you can make from here. Suppose that hydrogen only 2 electrons are there, so only one figure you can make like this. Okay, now these are the questions which are asked. Okay, what is the bond order, what is the bond dissociation energy, what is the bond length, paramagnetism and diamagnetism. Order of bond length, not the value of bond length, right? So there are few more exceptional compound we can see here, like if you consider C2 molecule, right? How many electrons are there? 12 electrons. Now do the electronic configuration of C2 molecule. So sigma 1s2, sigma star 1s2, after that sigma 2s2, sigma star 2s2, sigma star 2s2, right? So what order should we should follow? We should follow the order less than 40. So pi degenerate orbital, pi 2px, pi 2px, right? So and pi 2py. How many electrons are left? 2 to 4 to 6 to 8 to 10 to 12. So this type of filling, Hund's rule you should apply. No unpaired electrons are there. 1, 2, 3, 4, 5, 6. So this is diamagnetic. Okay. What we can see here, that here pi bond is formed before the sigma bond, right? Before the sigma bond in this molecular orbital treatment. Although we are not getting this C2 molecule, means this is not a stable molecule. So this is a theoretical approach. Basically, molecular orbital theory is also a theoretical. Not necessary that every molecule fulfill all the features of this molecular orbital theory. So as per molecular orbital theory, this is possible, but in actual sense, there is no C2 molecule, known C2 molecule. Therefore, there is no point of worry for you, right? Whatever the question asked, okay, you can answer this. So if somebody asks, okay, is it possible that pi bond can form before sigma bond? So you can say yes, why not? In case of C2, when we treat this molecule as per the molecular orbital theory, pi bonds form before the sigma bond, because this is the energy order determined. So you have to answer the question. But in the real sense, this has no meaning, because there is no C2 formation of C2 molecule, right? Known C2 molecule. So see this configuration you can write in this way also. This K shell is complete, so here you can write somewhere, you may get this type of representation also, KK. So if you write this KK, then you can start from here, right? So sigma 2s2, sigma star 2s2, and pi 2px2 and pi 2py2. And from this configuration only you can calculate the bond order. You will get the same result, because this plus, this minus. So you can ignore. So what is the bond order here? Bond order is equal to 1 by NB. So 2 to 4 to 6 minus 2 is equal to 2, right? Bond order is 2 here. So from this part only you can do the calculate the bond order and do the electronic configuration. But you have to write like this: KK means K in K shell 2 electron, in K shell 2 electron. So total 4 electron here you have adjusted, right? So this is the treatment of C2 molecule. Now similarly you can do for other molecules as well. Here I have given you the homework and most of you have done this homework. Many of you have not yet submitted your homework. I don't know why all of you are so reluctant to submit the homework, right? There is very simple question this. Now if we take this molecule F2 molecule, so how many electrons are there? 9. So 9 and 9, 18 electrons are there. So we can write sigma 1s2, sigma star 1s2, sigma 2s2, and sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, and pi star 2p x2, pi star 2py2. 1 2 3 4 5 6 7 8 9, total 18 electrons distributed, right? All are paired, so this is diamagnetic, right? And what is the bond order? So bond order is equal to 1 by 2, 1 2 3 4 5, 10 minus 1 2 3 4 8. This is equal to 1. Suppose that someone asks, okay, draw the energy level diagram for this to show the formation. So how to make this energy level diagram? For this, see, we can start from here. 1s, see, one fluorine atom here, other fluorine atom is here, 1s and 1s, 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 both have same energy. So they overlap and forms two orbital. Right, both have same energy. So this is sigma, we can say G-rate 1s, and this is sigma u 1s, right? And also we can put star. So 2 electrons here, 2 electrons here, so 2 electron here, 2 electron here. Similarly 2s, 2s, both have equal energy. So here 2 electron, this is 2s, this is 2s. Here also 2 electron, so this is sigma 2s and sigma star 2s, right? 2. Now come to the 2p. So 2p, so here right, so 1 2 3 4 5. So 5 and 5 10 electrons, so here this is sigma 2pz, lowest energy, so put 2 electron. This is pi 2px, pi 2py, so 2 electron, 2 electron, so here 4 electron distributed. Now come to here, this is pi star 2px, this is pi star 2py, 1 electron first with a parallel spin as per the Hund's rule. Now 1. So I think how many electrons? 5 here, 5 10. So 2 2 4 2 6 2 8 2 10. So all are paired, right? And this molecular orbital is empty. So one nomenclature is using here. We so see this sigma 2pz, which is unoccupied. So this is called highest unoccupied molecular orbital. See, highest in what term? Highest in terms of energy, right? So if the question is asked that tell the highest unoccupied molecular orbital. So in this molecule, F2 molecule, the highest unoccupied molecular orbital is sigma 2pz. This. Okay. See, this is highest occupied, right? This is no. This is wait. One correction is there. This is LUMO, lowest unoccupied molecular orbital, because this could not be highest, because some more orbital than this may be there, but this is LUMO, lowest unoccupied molecular orbital, and this is what the highest occupied molecular orbital. So HOMO, highest occupied molecular orbitals are pi star 2px and pi star 2py. Right, now it is okay. So this is highest occupied molecular orbital, this, and this is lowest unoccupied molecular orbital, because there are some energy levels and some orbitals are possible which are also unoccupied, right? So these two are named like this also. So this word you may get somewhere when you are reading the books or any literature. So this is the representation of this electronic configuration here in the energy level diagram, right? So this way you can construct the energy level diagrams for different molecules. So you have to do practice for this, that construction of molecular orbital diagrams. Right now, I am taking HF molecule. It is, a heteroatomic molecule. So the question arises that can we use this, energy order what we have made for this simple diatomic molecules? So the answer is may or may not. In some cases we can use, but not in all cases. So can we write the electronic configuration for this HF? So see, how many electrons are there? 9 and 110 electrons are there. So first sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and 10 electrons. So pi 2px, pi 2p y1, x1 and y1. So 2 to 4 to 8, so 2 to 4 to 6 to 8 to 10. So this is total 10 electrons. So if you see the formation of this molecule, are you convinced with this electronic configuration? Hmm? That 1s of this fluorine, 1s of hydrogen, hydrogen has only one s. So 1s of this hydrogen will overlap with 1s of this fluorine. After that, is there possibility of any overlapping, or 1s of this hydrogen will overlap with which orbital? Can we say? So it is very unlikely that we can do this electronic configuration for a heteroatomic molecule like this HF. So I have some experimental energy order for this HF molecule, and see, all of you can see this. See, this is what HF molecule, and try to understand this diagram. See, so if you see here, this is hydrogen. Hydrogen 1s energy, energy of 1s orbital of hydrogen. See here, electron of 1s of fluorine, it is not shown here. So basically the energy of 1s of hydrogen, see, this is the exact energy diagram. Energy of 2s, 2p, right, and 1s of fluorine is much smaller than the energy of 1s of hydrogen, because as the effective nuclear charge increases, the energy of these substance, it is decreases. So the energy of 1s and 2s and 2p of fluorine is less than the energy of 1s of hydrogen. See, this is the reason why in valence bond theory it was argued that this hydrogen will overlap with the 2p of what? Fluorine, not with 1s or 2s or with any other orbital. Now see, so if we represent here fluorine, and if we see 1s of fluorine will somewhere will lie here. So this is also have two electrons. So here two electrons, and this is also non-bonding, right? So this two electron, if we show this two electron is this, then 2s electron is shown here. This is also a lone pair, right? And see here, this 2p orbitals, they are non-bonding, right? So what will happen? No, don't show this 1s because this is in the core, right? Here we show only the valence shell, so don't show this. Only with this valence shell configuration is here. 1s I am not considering here for fluorine. So this is non-bonding, so non-bonding lone pair, and 2 here non-bonding, so 2 lone pairs are seen here. So these are present in pure p atomic orbitals, and this is only sigma bond in which one electron of fluorine and one of hydrogen. So what valence bond suggested, that is what true here. No need to this molecular orbital theory to explain this, because you cannot say that a hydrogen, this 1s will go to overlap to the 1s of fluorine. It is not possible. See the difference in energy. Its energy is even more than 2p. So there is a huge difference between 1s of fluorine and 1s of hydrogen. And this is a very important point of this molecular orbital theory, that energy of orbitals is comparable, right? Then only overlapping is possible. So this molecular orbital theory is very important regarding this, that which lone pair is, which pair of electron is non-bonding, and which one has the bonding. So here you can see very clearly that non-bonding orbitals, basically they are atomic orbitals, right? They are atomic orbitals. So non-bonding orbitals also exist, because there is a mismatch here. There is a mismatch in the energy. That's why this is non-bonding molecular orbital is here we are considering this. So non-bonding situation arises due to two reasons. One is if the large difference in energy is there if in the molecular atomic orbitals, and second one is due to improper orientation, means symmetry non-allowed situation. So there are two reasons for the existence of non-bonding molecular orbitals. One is huge difference in the energy, and second one is the orientation, right? So in this way you can explain the formation of HF molecule. So this treatment, this treatment is not applicable where? Here, see, is this as per this treatment, if you use this energy level diagram or molecular energy, then it is paramagnetic, but here actually it is diamagnetic. So you cannot use the above energy orders, or above that energies of molecular orbitals for explaining the heteroatomic molecules, right? So this is always applicable, this order what we have here. This is for homoatomic. See here, it is clearly written homonuclear molecules. See here, it is written here homonuclear molecules. If you have copied this figure as it is in your notebook, then definitely you have copied this also. Homonuclear molecules means this order is not valid for heteronuclear molecules. But some people try to use this, model for heteroatomic molecules and try to explain something, but that is wrong. That is wrong. Many people doing this mistake. So that's why I'm trying to explain you the best. I mean, with the help of this example. Now, again, I am taking one more very important molecule, that is carbon monoxide. Everybody is doing mistake here to explain the molecular orbital treatment of carbon monoxide. Everybody is doing mistake. What mistake people are doing? See, they were explaining that it has 14 electron, and so the nitrogen electronic configuration is applicable here, sigma 1s2 sigma star 1s2 and sigma 2s2 sigma star 2s2 and then pi 2p x2 pi 2p y2 1 2 3 4 5 6, one more sigma 2p z2, right? So people are trying to use this energy, molecular orbital energy, to do the electronic configuration of carbon monoxide, despite this is a heteronuclear molecule. So what is happening? This is a diamagnetic. Diamagnetic, okay. So experimentally it was found diamagnetic. Okay, be happy that my this is working. Now come to the next. What is the bond order? Bond order is equal to 1 by 2 nb minus na. So 1 by 2, 1 2 3 4 5 10 minus 1 2 4. So this is 3. So experimental bond order, experimentally bond order is equal to 3. Very happy. Oh, my this calculation is working here. But now see, when it is asked that do the electronic configuration of CO plus. So if you do the electronic configuration of CO plus, it is 13. So sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 pi 2p x2 pi 2p y2 and sigma 2p z1, right? Now this is paramagnetic. Okay, very happy, because experimentally it is paramagnetic. And what is the bond order? So bond order is equal to 1 by 2 10, not 10, now this is removed from bonding, so this is 9 minus 4, it is 5 by 2 is equal to 2.5. Okay, so you are calculating bond order 2.5, and experimentally what we are getting, the bond order is equal to 3.5. Now what you can do? How to explain? So what people trying to explain you, many people are doing mistake here. Many people are doing mistake. And what they were trying to explain, okay, this is exception, so you have to remember this like that, right? So, but this is not the case, because this order basically what we have deduced from the for the this molecular orbital treatment. This is applicable only for this homonuclear molecules. So for heteronuclear molecules there is some difference, as you have seen here. In HF molecule everything is I mean different, right? You cannot use the simple I mean treatment of this molecular orbitals. So here this carbon monoxide, this is so fantastic molecule, and every time people trying to explain this molecule or ion as a exception. But now you can see I am showing you the exact experimental energy order of different molecular orbitals. And this 1s, I'm not considering here 1s, 2s, and this sigma. Basically, in actual order, in actual sense, here this sigma 2s, this anti-bonding molecular orbital has the highest energy. So now you can see, and from that order, you can very easily justify all your queries, and you can justify the experimental order and the difference between theoretical and experimental result. All you can explain. Now you can see here. Now you can see. See, this carbon and oxygen, Z effective of oxygen, Z effective of oxygen is more than carbon, Z effective of carbon. So if Z effective for oxygen is more, so the atomic orbitals of oxygen have less energy than the atomic orbitals of carbon. So atomic orbitals of oxygen have less energy, have less energy than the atomic orbitals of carbon, right? So see here, this is the energy order, and this this is the oxygen and this is the carbon. So 2s of this oxygen has the lower in the lower energy than 2s of carbon, and this is the 2p of oxygen and this is the 2p of carbon. Okay, now see, if you see here, then you will find that, see, this 2s of oxygen and 2s of carbon, they have energy more than pi 2px. So we can say that for carbon monoxide, what is the here we can write kk, right? Leave that, and this sigma 2s. That's why they have not written here. See, here it is written 1 sigma. 1 means sigma, not 1s sigma. This is first sigma bond, this is second sigma bond, this is third sigma bond. So first, second, third they have written here. See, in this sigma, suppose that if we consider this, so this is closer to the oxygen lone pair. So this is the reason why when we are drawing the structure of this carbon monoxide, triple bond is there, and oxygen have one lone pair. See, this lone pair, this has more oxygen character than the carbon character. So basically this is pure of this. And if you see, carbon also have one lone pair. Carbon also have one lone pair. So carbon monoxide, see, if you see here, this 2 sigma, this bond, this is closer to the carbon of 2s of carbon, so this has lone pair. So basically they do not have much overlapped character, rather they have the pure character. So but they are treated as a molecular orbital. Now pi 2px, so how to write this? Sigma 2s2 sigma star 2s2. Now after that pi 2px 2 pi 2py2, and then no, this is not this is this 2 sigma, this is sigma 2pz2, and here sigma star 2s2. That's why they have see here it is not written that which one is 2s, which one is 2p. So this 3 sigma, this is 3 sigma as per the notation here, and this is pi 2p, and this is 2 sigma, and this is 1 sigma. So this is the representation in this figure, right? Now if you want, you can calculate bond order. You will get the bond order 3, and if you remove electron from here, then you will get the bond order 3.5. So this is the experimental energy order of carbon monoxide. So this representation, this is not valid, for carbon monoxide, right? You cannot use this. You should use this order, right? So although they have shown here so many things, see in this orbital, see here this 2p character is coming. This is not you cannot say that this is for this and this. Okay, there is some correlation is there, but it is not pure. So this is the experimental order. Now you can calculate the bond order. Diamagnetic, yes, it is diamagnetic. Bond order 1 by 2, 1 2 3 4, 4 2 ja 8, minus 2 is equal to 3. And when you write CO plus, so this is equal to KK sigma 2s2 2s1, right? So now the bond order is equal to 1 by 2, 8 minus 1, this is equal to 7 by 2 is equal to 3.5, right? So in this way you can justify the molecular orbital of carbon monoxide, right? So if you see here, this is this pi star 2p, this is basically lowest unoccupied molecular orbital, LUMO, and this 3 sigma, this is highest highest occupied molecular orbital, highest occupied molecular orbital, and this is lowest unoccupied molecular orbital, right? So in this way, you can justify the formation of carbon monoxide molecule, right? So one thing is clear, that this electronic configuration and this energy level we cannot use for heteroatomic molecules like carbon monoxide, HF, NO, etc. Although NO have 15 electrons, many people are doing the electronic configuration by using that this configuration, because you know in N and O there is no much difference in their effective nuclear charges. Here carbon monoxide huge difference, HF is huge difference, but in NO the effective nuclear charge of N and O is very close. So up to certain extent this order you can use for that, but not exactly, right? Not exactly. So, although this is not in your syllabus, but see, carbon monoxide, why I have so much interest in this? My interest is this, that you should know the structure, because in coordination chemistry, this is a very good ligand, supposed to be very good ligand, and in that time when I will explain that here LUMO is empty, so it can accept the pair of electron from the metal, then you will not understand until or unless you have not gone through this treatment. Okay. So this is all about this carbon monoxide molecule and molecular orbital